So our next speaker is Naomi Leonard. She is the Edwin S. Wilsey Professor of Mechanical and Aerospace Engineering at Princeton University. Her research is on nonlinear control, multi-agent systems, and collective behavior in animal groups, and decision dynamics in mixed teams of humans and robots. And we'll be talking about humans now, right?
A little bit of animals and humans.
Animals and humans, great. Thank you.
Thanks very much. It's a pleasure to be here. I am going to talk about a theme in my research group which concerns using a systems theoretic approach to investigate mechanisms of collective decision-making. So by this I mean we seek to make mathematically rigorous connections between properties of the system and performance measures of the group. So the system parameters, the system features, and the measures of performance that we use are based on the kinds of understanding that people like Stephen and Jens have as to what's important in collective animal behavior. We're also looking and talking with people in neuroscience to understand what's important in decision-making in groups of humans. And so today what I thought I'd do was tell you a little bit about some recent work we've done on trying to unpack the questions of how accuracy in collective decision-making relates to the structure of the interactions, the network structure among the decision-making agents, as well as the location in that network of the different individuals that may have some leadership properties, like information or preferences about what they want to do. And the kinds of decision-making problems we look at are consensus decision-making problems. So these are very much like the ones we've seen in the case of fish or ants, where everybody is intending to make a decision, but to make the same decision. So they want to come to consensus about a decision among a number of alternatives. And they also want to be able to do this relatively fast and with great accuracy. So we've seen a bunch of examples, so I'm quite set up for this without having to go into detail. So animals need to choose together where to migrate, for instance. They need to choose together where they're going to move to if they're choosing a new nest site. If they're foraging, they sometimes choose together when to switch to a new patch. And moving together or deciding together not only keeps them cohesive, but as has been described, gives them additional speed and accuracy in their decision-making. So the kinds of groups that we look at are those that make decentralized decisions as individuals and rely on social interactions, so social cues in their decision-making. So I've shown you a snapshot from a video I'm going to show you a little later of a bunch of, these are actually dancers who have been instructed to use flocking-like rules. So they're moving around, and they've been told to stay arm's length from two other of the dancers as they move around and not let anybody else get closer. And so they move around in this kind of network-like structure, kind of like a school of fish. And these kinds of networks can be represented by a network graph, which I've illustrated on top of superimposed on top of the photograph of the dancers. So here there are 13 dancers, and each node in the graph is a green dot referring to each of the 13 dancers. And the arrows, the blue and red arrows, correspond to who's sensing whom. So this is the structure of the network. So there are two arrows from each dancer to the two that they're paying attention to, trying to stay arm's length from. And so this kind of network structure we can encode mathematically in a matrix. So this is just an array of numbers that refer to the weights that are placed on each of these arrows or edges in the network graph. So if there's no edge between, say, 10 and 5, the fifth by 10th element in the matrix is just a 0. Okay, so the last piece of the setup is that we also include leaders in the group. So there may be individuals who have strong preferences or may have particular information about what they're deciding on. So for instance, in a collective migration problem where everybody needs to sort of figure out where they need to go, and they need to agree on where they need to go, and then they need to move in the direction of migration, there may be some individuals who have some prior information, or some individuals who are vigilant and pay attention to environmental signals to figure out where they're supposed to go. And it's been shown in the literature, for example, this paper, 2005, and appeared in Nature by Ian Cousins and Jan Krauser, that just a few individuals are needed to actually lead the group in a correct direction, or to make a decision between alternative directions. And more recently, a very interesting question was asked in this context. So in the prior work, the leadership was imposed, so a few individuals were sort of assigned the role of having a preference or information, but more recently the question came up as to what happens when it's costly to invest in that information, or to acquire that information, or to develop that preference. So for instance, it's cheaper for you if you're one of the herd just to graze and pay attention to your neighbors, and it's more expensive to lift your head and be attentive to figure out where you're supposed to go. So the question was, given that it may be costly to invest in acquiring this information, what are the mechanisms and what are the conditions under which individuals will actually invest? And so they took the perspective of an evolutionary dynamic to try to understand how evolution of leaders and followers comes about. And so here's a little example of an evolutionary simulation in this context, where each individual is associated with, say, their direction where they're trying to move. If they're trying to migrate in a true direction, XI is the individual's current direction. KI is its adaptive strategy. So KI refers to how much it's investing in acquiring information about where it's supposed to go. So for instance, this is its update equation. It's updating its direction based on sort of a directed update. Given how much it's investing, it's going to just drive in that direction to migrate. So KI weights how much it invests in that activity. And then there's the social aspect. So it will also take advantage of cues from its neighbors and move along with its neighbors. And so it does that with a weight that's 1 minus KI. So it's sort of a net sum here. If it's paying attention to the environmental signal, it's not paying attention to its neighbors, vice versa. If KI is 0, then it's not paying attention to the environmental signal and it's relying on social cues. And in the adaptive piece of this, it's going to adapt its strategy, how much it invests, based on how well it's doing and how much it's costing to invest. So the benefits associated with this have to do with how well it's making progress in the true direction. So this is the steady state variance about the true direction. So this gives us a sense in terms of benefit of progress in the direction of the true migration field. And this is its cost, so it's proportional to how much it's investing by some kind of scalar constant C. So C represents just how costly it is. So individuals in this dynamic adapt their strategy to balance these benefits of doing a job and moving in the correct direction versus paying the cost to invest. And what was shown in this work was that for certain conditions, so a costly enough investment, after a certain amount of time, you get this splitting between those who invest and those who turn it off and just rely on social cues. And so one of the first questions we asked after we saw this work was, under what conditions will we see, or which individuals as a function of who's sensing whom, where they are in the topology of the network, will be the ones that make the investment? So where will leaders emerge in the network structure? And so we studied that, and we tried to study this analytically. So we wrote down the equations for the adaptation of Ki as a function of the fitness, which we could write in terms of all of the strategies of everybody, so that we could analyze the dynamics of a very simple update equation. So rather than using the full evolutionary dynamics, we have individuals just doing kind of a greedy climb on their performance. So they're investing if they have to, if they're not doing well, but if they're doing well, maybe because their next door neighbor is investing, they'll reduce their strategy because that's less costly, okay? And so we studied this in a lot of different contexts, and I'm just showing you a little example here where you're looking at the time evolution of the strategies of all the individuals, and this is a group of 10 individuals as a function of time. Here the warm colors refer to lots of investment. So the individuals who are up close to 1 are investing in the signal and not paying attention to their neighbors, whereas with the blue, they're just relying on the social cues. And so what we see here for this particular network topology, where there's one special individual who can see the other 9, and the other 9 can only see this one special individual, when the cost is relatively low to invest, all of the 9 fringe guys do the investing. It's cheap. Why not? The guy in the center doesn't bother because he can see all 9 of them, and why bother in that case? When the cost goes up a little bit, they all invest partially. So they're all doing a kind of maybe half paying attention to the signal and half paying attention to their neighbors. And then when the cost gets really large, only the center guy invests and all the fringe guys turn it off. Kind of interesting. So the question we then set out to answer was, that's all well and good that we can understand from an evolutionary point of view or from a sort of a greedy search kind of point of view what individuals would do to optimize their own cost-benefit analysis in terms of investing versus relying on the cheaper social cues. What if we ask the question, given a network and given the opportunity to choose, say, M individuals who would invest or who would be endowed with this property of being leaders because they were given information or preferences, which ones would we choose for the purpose of making the group most accurate at the level of the group in coming to consensus about a decision? Okay, so we call this an optimal leader selection problem. And so it looks kind of like this. So here's again what we saw before, that each individual has its, say, which direction it's trying to move, and it's updating its direction based on 2 signals. One is its update to move in the direction of the noisy signal that it measured from the environment, which I'm calling mu, that's, say, the true direction. And then another signal that has to do with just relying on the social cues, and we use this encoding of the network graph here. Okay, so I've changed this a little bit because now this investment doesn't affect your social cues. You're always going to pay attention to your neighbors. It's just whether you're going to invest in the environmental signal. So we asked this question, if we have M leaders and we have the rest are just followers where they turn off their investment, we want to find the set of M such that we have the greatest consensus decision-making accuracy. And here that's defined formally to be at steady state, we sum the variance of each individual's steady state variance about the true direction. And that gives us, we want that to be smallest. So by maximizing accuracy, we want to shrink the dispersion of the group about the true direction. Okay, so to do that, we use, we have derived a method to solve this problem using this metric. It's a graph measure that's referred to as information centrality. So it goes as follows. If you define the inverse path length, so from any node I to any node J, and then you look at as the information between those 2 nodes, 2 agents, and you sum all of this, that gives us what we call the total information between nodes I and J. And then information centrality is simply the harmonic average of the total information of every other node to node, say, I. So CI is its information centrality, the information centrality of node I. It's the harmonic average of the total information between every other node J and itself. Okay, and it's interesting to note that the inverse of this total information is actually equivalent to the resistance distance between nodes if you make the analog between a network and an electrical network. And this makes it really useful, so you don't actually have to go and enumerate every single path between nodes in a network. You can compute it simply based on that original matrix that encodes who's paying attention to whom. Okay, so as a result, we can compute all these things very easily. And so what we did to solve our original problem, which was how to choose the M optimal leaders who will maximize accuracy, so minimize that dispersion about the consensus decision, we extended this notion of information centrality to something called joint centrality. So we don't want to just know who is getting, lots of information or providing lots of information. We want to know pairs or triplets or quadruplets, because we want to think about the general case of M possible leaders. Okay, and so we define this notion of joint centrality, which I'll tell you in a second, and we define it explicitly so that the set with the maximal joint centrality, the set of M leaders with the maximal joint centrality, is the one that maximizes accuracy. And so then we can interpret that and show that in the case of a single leader, if you're picking just one, it is the one. You should pick the one with the highest information centrality. In the case of a pair, this optimal joint centrality looks like the sum of, well, it looks like this, which has to do with making sure that each individual has high information centrality on its own, also making sure that the resistive distance between those two is big, and then also making sure that lots of others are close to one or close to the other. So it's like a coverage kind of thing. It's very intuitive. You want individuals who have high information centrality themselves, but you want them to cover the graph well. This is the formal way to write it down, at least in the case of pairs, and we can write it down more generally. Just to kind of give you here's a little illustrative example. So here are our 7 nodes. If you want to pick one leader, you should pick B. This is the one with the highest information centrality. If you want to pick 2 leaders that will maximize accuracy for this group to make consensus decisions, if they can only invest sort of a small finite amount, they're going to be affected by noise, and you should pick D and C. If, however, they can invest quite a bit, then noise won't play such a role. Their investment will dominate, and you can pick pairs E and F. Here's another little example just to sort of illustrate. This is an example of a very large protein network. So this is a group of genes called YeastNet. There are something like 5,800 nodes in this network, and the biologists look for pairs of nodes, pairs of genes that through the various processes that connect them lead to what they call synthetic lethality. So when they're both mutated, the cell dies. And so we took their data and we computed over all possible pairs in this network where there are 360,000 edges. We computed the joint centrality, and then we did the same for all the identified pairs that are synthetically lethal, and we saw that they have this disproportionately high node pair joint centrality. So that's another example. But one can also look back at those emergent groups of leaders that we saw from the earlier story. So we can then ask the question: were the individuals that emerged optimal in any sense at the level of the group in terms of the group making accurate decisions? And so in the case of the example that I showed you, if you're going to pick one leader, and this is obviously intuitive, but you should pick the one in the center, right? This is the most information central. But then you can write down explicit formulas for other kinds of networks. So in the case where everybody's kind of in a line, which pair should you pick, if you're picking a pair, to be, say, vigilant or to pay attention to the signal so that the group, through the information process, spreading process, will make the most accurate decision. It turns out that you can write down explicitly. So for high numbers, it'll be sort of 20% in from either end of the path. Okay, and this is quite interesting, and we're actually using this in our conversations with a colleague, Dan Rubenstein at Princeton, who studies zebras and looks at data to understand who's being vigilant. So when do the zebras have their heads up and when do they have them down? And he's interested in which ones and how many and where they are and he looks at lines of zebras. So then we also asked this question in the context of this recent data that we collected on this story of dancers that I briefly mentioned. This is a project that I did with a colleague in dance. She's a choreographer, and she runs the program in dance at Princeton, Susan Marshall. We used dancers to try the kinds of rules that we use to model collective motion in animal groups. And so I'll just turn this on. I only have 1 minute. So here these dancers are trying to stay arm's length from 2 others and not let anybody else get closer, and we get all this really kind of incredible schooling behavior. We have the walls that they obviously don't run into. And we videotape this, and we wanted to ask, the question, once we kind of were inspired by our analyses, what was the story with respect to the centrality of individuals in the context of these motions, and how did that relate to the way the group moved spatially? And so we digitize the video, we can track the individuals, we can figure out where they are, we can estimate who's paying attention to whom, and so we can write down the networks, and we can compute things about the networks. And so what we computed here is close to information centrality. It's something called node status, and we were able to show that node status was correlated with what we think of as influence or leadership. So when the group turned, those with high node status were leading the group in terms of the sort of turning behavior. And so when we plotted for our 13 dancers, this average status that they had over the course of a track period of 72 seconds, we saw something really interesting, which was that the distribution was very, very large, as compared to what would happen if you modeled these rules with particles. We saw basically outliers. We saw individuals who were clearly initiating kinds of movements and being followed. And so this was quite interesting. We attribute this to human bias, and we dug a little bit further, and some of our preliminary results show some very interesting things that we're hoping to study, which was that some individuals are sort of towards the front and seem to lead from the front physically. Some, like node 12, seems to lead from the center of the group, and we even found a node that is kind of like Dan tells me, the male zebras that will lead from the back. So these are sort of where we're heading now to try to understand these kinds of stories and try to understand some of the differences in personalities between these people and the strategies that they use, whether they just dance well or whether they behave differently and carry out rules differently. Okay, so I'm out of time, but just to summarize, we did this analytic investigation of the connections between leadership and performance as a function of measures of the network, using it to develop testable predictions and hypotheses. I'm also using it in the context of design and control of engineered and robotic networks. Some ongoing work has to do with some new results on effective resistance in directed networks. We've also expanded our study not just to accuracy, but to speed accuracy trade-offs in decision-making between alternatives. And this is sort of to come, some exciting new work where we're looking at the role of the network structure and leadership in a dynamical systems analysis to see how bifurcations unfold as a function of who's sensing whom and where leaders appear. Okay. Thank you very much.